So far in the course, we've been analyzing most of our thermodynamic processes and devices by using the conservation of energy equation, otherwise known as the first law of thermodynamics. And even though this very powerful tool has been enough to solve for the system characteristics of interest to us, this first law doesn't restrict the direction of how that energy is conserved. The second law of thermodynamics focuses on the direction of natural processes. It restricts our analysis of the energy conservation by telling us that a natural process can only run in one sense, and it's not reversible. Picture dropping an ice cube into a glass of warm water, and for a minute, just forget about the surroundings of the glass of water and the ice cube. Maybe picture them as completely isolated by a 100% efficient insulating wall. We know that because the heat going from the water into the ice cube is the negative version of the heat received by the ice cube from the water, the total change in internal energy of the ice cube will be equal to the total change in internal energy of the water. The first law of thermodynamics, this energy conservation equation, allows us to see that. The energy from one body, in this case the water, goes to the other body, the ice, to melt it and make it become water, and the water itself loses internal energy and becomes colder. But with the first law only, we would not be able to guarantee that the ice cube could become even colder while the water becomes even warmer. This energy conservation law could very well be applied to state that the change in internal energy of the ice cube as it becomes colder and colder is the same amount of change in internal energy of the water as it becomes hotter and hotter. Of course, in this simple example, we don't need an entire law of thermodynamics to know that the second case is simply not physically possible. But in general, that is indeed what the second law does, at least qualitatively. One of the most important quantitative benefits that the second law of thermodynamics offers is related to the entropy. We've seen values for specific entropy S in some of our property tables, but we'll get to that later. Let's go back to the ice cube type examples. In a slightly less obvious scenario, still very obvious though, we know that we can, for example, add work to a tank with a fluid in the form of a rotating paddle wheel to make its contents heat up and have the system put out heat to the environment. From the first law perspective, we could very well say that we can do the opposite, that we can add heat to the fluid and extract work. But we know that this is not possible. Just because the contents of the tank are becoming hotter, the paddle wheel is not going to start rotating spontaneously. And this is easily seen with the help of the second law. The second law attaches a quality or value to the different types of energy. When looking at different types of energy from the first law perspective, we don't care if it's thermal or work or kinetic energy, they're in practice interchangeable. The second law actually tells us which one has a higher quality or value. So with this example of the paddle wheel, we understand that a single process can be irreversible. However, we can have a similar situation where in practice, we can in fact extract work out of adding heat to a system. So we'll come back to the second law of thermodynamics in much more detail later, 2 lectures after this one, link below, but for now we'll focus on a couple of particular systems where we can engineer our way into turning heat into work. For example, let's assume a closed system, a piston cylinder system where we bring in a mass, let's say the conveyor belt drops it at the top of the piston, and by heating the gas inside of it, we bring the mass to a higher altitude. This is effectively using thermal energy to gain potential energy, or what is the same, to extract work from the system. What if we want to start over? What if we want the piston to go back to its initial position, so that the next mass that is coming in from the conveyor belt can also be brought up using the piston? Well, we could cool down the gas inside the system, right? And this doesn't necessarily mean that we're subjecting the system to, let's say, a flame and then cooling it down by blowing on it, right? We can have a high temperature reservoir provide the heat to the system in step 1, and a low temperature reservoir take the heat from the system in step 2. The term reservoir refers to a source so big that removing or adding energy to it will barely change its properties. If we have a drop of water that we add 10 joules of heat to, the temperature of the drop will probably change by a couple degrees. But if we add 10 joules of heat to a lake, its temperature might just increase by so little that we wouldn't be able to measure it. In other words, reservoirs are sources that in practical terms maintain their properties even when adding or removing energy from them. A system like this, where we add heat from a high-temp reservoir, extract some energy from it in the form of work, and then bring it back to its original state by rejecting the remaining heat using a low-temp reservoir, and repeat this over and over, is what we call a power cycle or a heat engine. The most common example of a heat engine is a steam power plant, which operates on a Rankine cycle. We'll learn more about this soon. In a steam power plant, we first have a high-temperature reservoir that supplies heat to a boiler. A boiler can be interpreted as simply as the pipe flow device we studied 3 lectures ago, linked below. We have liquid water flowing through a pipe and we add heat to it to obtain steam. State 1 and State 2 would go before and after the boiler with no significant changes to kinetic energy or potential energy, plus the assumption that the process occurs at a constant pressure. From 2 to 3, the steam goes through a turbine, which we already know allows us to extract work while decreasing the substance pressure and temperature. From 3 to 4, we'll pass the fluid through a condenser. This condenser rejects heat to a low-temperature reservoir, and it can be considered as another pipe flow device where there's no significant changes in kinetic energy or potential energy, and just like the boiler, we keep the assumption that the process occurs at a constant pressure, only this time the constant pressure is a low pressure as opposed to the pressure in the boiler. So how do we bring back our fluid from State 4 to State 1? Well, from the name that we're giving the second pipe flow device, the condenser, you can probably infer that that rejection of heat will allow the steam to go back to a liquid water phase. So if the main difference between States 1 and 4 is the pressure, we can bring it back up with another one of the steady-state devices we studied in the second lecture video of the 3-video series, also linked below. That device would be the pump. Of course, this pump requires some work input for it to work and cause the water to gain pressure, and that's why this cycle will have a net work out. The work we obtain from the turbine minus the work we need for the pump to operate. And of course, the work coming out of the turbine has to be greater than the required work to run the pump for the cycle to be worth running. Now, we know that we can set our control volume to be whatever we want. So what happens if we decide our control volume encompasses the entire cycle? Well, from the first law, or energy conservation equation, we know that the change in internal energy is equal to Q net minus W net. There is no mass coming in or out in this case because for this control volume we selected, it is a closed system. And since after one cycle the water goes from State 1 to State 1 again, the change in internal energy is 0. Therefore, the net amount of work is the same as the net amount of heat transferred. Following the same sign convention that we always use in thermo, W net is W out minus W in, and Q net is Q in minus Q out. The efficiency of cycles like these, and this is going back to one of the first lectures of this course, which are usually defined as how much work you're getting out of the amount of energy you're putting in, would be W net over Q in, or using the expression we just obtained, Q in minus Q out over Q in, or 1 minus Q out over Q in. Let's look at an extremely short and easy example that focuses on efficiency, something that we had covered in some form before. And if you'd like to check other examples on heat engines or power cycles, make sure to check the links to those in the description of this video. A steam power plant receives heat from a furnace at a rate of 320 gigajoules per hour. Heat losses to the surrounding air from the steam as it passes through the pipes and other components are estimated to be about 12 gigajoules per hour. If the waste heat is transferred to the cooling water at a rate of 170 gigajoules per hour, what is the net power output and the thermal efficiency of this power plant? To solve this problem, all we need to know is how much heat is being lost. Out of the 320 gigajoules per hour that the plant receives, 170 goes to the water, the low temperature reservoir, and 12 goes to the pipes and components. Therefore, only 138 will be converted into usable energy, and that will be the net output. As for the efficiency, we defined it as workflow net over total heat in, or 138 over 320. This results in 43.1%. And that's it. Like I just mentioned, if you want to see other examples on the power cycle topic, make sure to check the links below, where you'll also find links to all the other lectures of the thermodynamics course, as well as playlists to other engineering courses. Thanks for watching.